All right, guys, welcome back to week 7, Equilibrium and Elasticity. So again, go ahead and sign in below at the link that I posted. And if you have any questions, comments, anything that you want me to change, go ahead and put that below. I know we're coming towards the end of the quarter, end of the year, so let me know. All right, so let's do this. Number 1. So 50 kilograms child sits on a seesaw 4 meters away from the point where it pivots. The mass of the bar supporting the box is 15 kilograms. Where should a 35 kilogram child sit to balance the seesaw? What is the normal force exerted by the pivot point? Okay, let's start by drawing a diagram. Okay, so we got our seesaw. And on one side, let's say the left side, we have this 50 kilogram child. Right, 50 kilogram child, that is 4 meters away from the pivot point. Okay, then we have another child. That is 35 kilograms, and we don't know this distance yet. That's what we want to find, right? We want to find the distance that the child is away from the pivot point so that we can have our system in equilibrium, right? So that seesaw is balanced. Okay, so the first thing that I'm going to do is, so let's draw out our forces. So we have the force of the 50 kilogram child, right? So let's call that force 1. And we have the force of the second child, force 2. And we have the force of the bar, right? So let's say the center of gravity of this bar is right here at the pivot point. It's going down, force gravity. And the pivot point is also pushing up on the bar, right? So then we have the normal force normal. Okay, now that we have all of that written down, let's go and let's see, what do I want to do first? Normal force. Yeah, so the first thing, let's calculate the normal force first. So what is a normal force? So the normal force exerted by the pivot point. So what is that? How do we calculate that? So essentially what we have to do is we have to add up all these forces together. And since we know that our system is in equilibrium, the F net in the y direction is going to be 0, right? So we know that F net is 0. Okay, so if we make our F net equation for the normal force, it's going to be what? The normal force minus, let's say the negative direction is downwards, so the normal force is going upwards, so it's positive, minus the F1 minus F2, and then also the weight force, right? So the force due to gravity, and this all equals 0. Okay, so now when we solve, we can just solve for the normal force. So then essentially we can just take all these variables to the other side, equals F1 plus F2 plus Fg. Okay, so we can find all those values, right? So the normal force equals F1, which F1 is 50 times 9.8, right? So just write out 50 times 9.8. Then F2 is 35 times 9.8, and then force due to gravity is 15 times 9.8. Okay, so that'll all give us our normal force. So our normal force here in this situation is 980 newtons. That is our normal force. So that's how much this little pivot point here has to push up on that bar to keep it balanced. Right, so then the second question here is where should the child sit on the seesaw, right? So where should this child sit on the seesaw? So, so how do we do this then? So now we have to essentially find like the torques that each child is putting on the system, and we have to make them equal to each other, right? Because the only forces really acting on the system when it comes to like balancing the seesaw are the two children, right? The two children, because the force of the bar, the center of the gravity is above the pivot point. So the force normal and the force of gravity are sort of like canceling out here. Like they're not a part of the system when it comes to balancing the seesaw. So what we have to do for this part is we're going to make up another equation, right? So, or what I should have said is the force due to gravity doesn't create a torque. That's a better way of putting it. So essentially what we're doing here is we want F net to equal 0, right? We want the ending torque to equal 0. So we're going to say torque 1, which is just what that 50 kilogram kid is. And torque 1 is going in the positive direction, right? Like I said before, it's sort of tracing positively around the unit circle, or you can think counterclockwise is positive, so it's pushing the counterclockwise direction. And the second force is pushing a negative, to where I'm negative torque, it's pushing clockwise. That equals 0, right? So then when we solve, so torque 1 equals torque 2. So then we can find these torques by, so the force, so let me do 50 times 9.8 is the force of the first guy. So 490, and he is 4 meters from the center, right? So that's how you get the torque for the first child. And the second child, he weighs 35 times 0.8. So this is the force they are exerting, and we don't know how far it is yet, right? So then it's pretty simple. You just solve for x times 4 divided by 343, and you get a distance of 5.714 meters. So that's how far the second child has to be away from the center to keep the system balanced, right? It makes sense because the second child weighs less, so you'd want to have it further away from the pivot point to exert more torque than the first child, right? Cool. So go on to number 2. Okay, so number 2. So for number 2, 4 kilogram bar lays on top of the pivot point with the center of gravity 1.5 meters to the left of the pivot point. A box is placed 1.5 meters to the right of the pivot point to balance the bar. How much does the box need to weigh to keep the bar from falling off the pivot point? All right, so let's draw this. So we got our pivot point, and then we have this bar, okay? So it says the center of gravity is 1.5 meters to the left. So I'm going to draw it looking like that, right? And then let's say the center of gravity is like about right there. And then we have a box placed another, 1.5 meters to the right. So a box right here. So this is 1.5, and then this is also 1.5. 1.5 meters. Okay. So now what do we do? So it's kind of similar to the first one, right? You're trying to balance the torque of each force acting on the system. So let's write out our forces. So what forces are acting? So we have the force of the bar acting, right? So the force due to gravity of the bar, and we draw that from the center of gravity. And we also have the force of the box, right? Force of box. Okay. So now, we just calculate the torques of each and make sure that they balance out, right? We want our system to be in equilibrium. So we want F net to equal 0. And if F net equals 0, then we want the torque of the gravity, right? Which is in the positive direction, minus the torque of the box, to both equal 0, right? And I put a minus sign again because the torque to the box is going in the negative direction, or going clockwise, which we define as negative. So then when we do this, we know that the box weighs 4 kilograms, right? So 4 kilograms times 9.8, and it is 1.5 meters away from pivot point. And then so then I'll solve, so I'll rearrange it, right? So torque G equals torque box. So this is torque G equals torque of the box. The torque of the box, how much does the box weigh? Box, oh, we don't know how much the box weighs. Okay, so let's say X times 9.8, right? Times 1.5. Okay, and then when you solve this all out, what you should get is, let's see, 1.95. Okay, and then divided by 9.8 times 1.5. So X should be 4 kilograms. All right, so number 3, my screen is frozen. Hold on. All right, cool. So number 3, a force of 300 newtons is required to stretch a spring by 24 centimeters. How far can a force of 750 newtons stretch it? Okay, so essentially what we're going to be doing here is using this equation, right? So K equals force over like displacement, right? So this constant equals the force over displacement. So we want to find like the constant of this spring. And then if we find the constant of the spring, then we can apply it to whatever force, right? And find whatever distance that it's going to make. So let's find it using the first situation. So we have a force of 300 newtons. It's required to stretch a spring by 24 centimeters. And let's just convert 24 centimeters to meters. So that would be 0.24 meters. And then when you calculate it, that gives you the constant of 1,250, right? So then now we have this constant, and we can apply it to a situation where we have 750 newtons of force, right? And that'll give us some displacement value. So when you calculate that now, that'll give you a displacement of 0.6 meters, right? So we added more force to it, so we got a larger displacement. That makes sense, right? When you're adding more force to a spring, you're going to get a larger displacement. And this is just a constant. This is sort of like how strong the spring is, pretty much, right? A stiffer spring, it's not going to move. It's not going to have as much displacement than if you were to have a lower constant on the spring. So that's the concept behind this. Okay, number 4. So a 300 kilogram block hangs on a 2 meter long aluminum cylindrical rod with a diameter of 0.5 centimeters. The elastic modulus of aluminum is that number. So what is the change in length of the rod? What is the new length of the rod? Calculate the tensile strain on the rod. Okay, so A, let's start with it. What is the change in length of this rod? Okay, let's actually before I do, let's draw this out. So we got a rod, cylindrical rod. Okay, this is cylinder, whatever. And then we add some 300 kilogram block to it, right? So we add some pressure, some force to the end of it, and that stretches it. So this is the new rod after it's stretched. Okay. So this is after we add that block to it. So originally, it's 2 meters long, right? 2 meters long, and it has a diameter of 0.5 centimeters. And then it has the Y value of 70 times 10 to the power of 9. Okay. So, and then we have, so this is the initial length, and then we have this final length right here. Right, so the length final. And then this distance from the initial to the final is delta L, right? So for part A, we want to find delta L. What is the change in length of the rod, right? So we want to find delta L, and we have an equation that's that'll help us do that. So we have delta L over the initial length of the rod equals the force exerted on the rod divided by the area. So like sort of the area of the cylinder, divided by this constant, right? So the elastic modulus. Okay. So now what we do, I'm going to solve for the change in length. So change in length equals, and I'm going to write this as 1 over y times f over a, because it looks prettier, and then times that. Cool. So we have this equation. So now all we do is we plug in our values, right? So we know that we have our constant, right? So the elastic modulus, which is just specific to that metal, right? Aluminum, 70 times 10 power 9. And then the force exerted on it, so it's a 300 kilograms. So we added a 300 kilogram block, and then times 9.8, that'll give us force. And the area, so the area of this cylinder, or at least area of this like face of the cylinder. So it has a diameter of 0.5 centimeters. So we know that has a radius of 0.25 centimeters. And if we convert that to meters, that's 0.0025 meters. And then we want to find the area, right? So the area of a circle right here, which is what it is pi r squared, right? So the radius is 0.0025 squared. Cool. So we'll just plug that in here, 0.0025 squared, and then the initial length, which is 2 meters. And when we solve, we're going to get a change in length of 4.278 times 10 to the -3 meters, right? So essentially what that is saying is our rod changed by 4.278 times 10 to the -3 meters, which is very, it's not that big, but is a change. So that is the change in length. So when we go to part B, we want to find, what do we want to find? The new length of the rod. So how do we find this new length of the rod? Well, it's pretty simple, right? We just add the change in length to the initial length. So the initial length is 2 meters plus 4.278 times 10 to the -3. And that'll give us 2.00427 meters. Cool. And then part C is calculate the tensile strain on the rod. Okay, so how do we calculate the tensile strain? So the equation for tensile strain equals delta L over L. So essentially it's the fractional change of the length of the rod, and that's how much strain we put on it. So when we calculate it, that's just 4.278 times 10 -3 over 2 equals 2.139 times 10 -3, right? That's a strain that we put on this rod. Cool. All right, number 5. So it's pretty similar to the last one, except we're using a cube. So a cube with a side length of 10 centimeters is made up of aluminum metal with an elastic modulus, so like a Young's modulus, what we say in class, of 25 times 10 to the power of 9. Horizontal shear force of 50,000 newtons is applied to the cube. How far will the top of the cube move in the horizontal direction relative to the top of the cube? To the bottom of the cube, sorry. What is the shear stress applied to the cube? Calculate the shear strain. Okay, so this is the diagram of what's happening. So we have a force of 50,000 newtons being applied to this cube, right? And the length, right? So one side of the cube is 0.1 meters or 10 centimeters, converted it. So what happens is we apply a force to the top of the cube, and the top of the cube sort of like bends, right? So the bottom of it is glued pretty much to the surface, and the top just bends, right? So we want to find, in part A, we want to find how far the top of the cube moves in the horizontal direction relative to the bottom of the cube. So same equation, right? Delta L equals 1 over y times F over A times L, right, the initial line. Okay, so it's kind of plug and chug. So we got delta L equals 1 over 25 times 10 to the power 9. And then the force being exerted, 50,000 over the area. So what's the area of a square? Well, it's just the length squared, right? So it's 0.1 squared. And then the initial, what's called the initial length is 0.1 meters. So when you calculate it, you get a delta L of 2 times 10 to the power of -5 meters, right? So that's essentially how much it bent. Is yeah, it's like really small value. It's like 0.02 millimeters. Okay, so then part B. Now for part B, it wants us to calculate the shear stress applied to the cube. So shear stress. So this is different from strain. So you gotta know the difference between stress and strain. So the equation for stress, that's how much force we are exerting on the object, right, the area of the object. So the larger force we put on this object, the more stress it is, right? If we increase the area that we're putting this force on, we're gonna have less stress. So it's pretty simple calculation. You just plug in your force value and then your area, 1 squared. So that gives us like 5 million newtons per meter squared. So that's how much stress we were putting on this cube when we were putting that much force on it. So then part C is calculating the shear strain. So the shear strain. So strain is delta L over L, right? So just like we did in the last problem, this is strain. So this is pretty much the how much it changed in length, the fractional change in length. So we know that the change in length is that, and then the initial one is 0.1. So when we calculate it, that gives us 2 times 10, -4, right? Yeah. So that's the strain. That's how much strain we pushed, we exerted, right? After the fact, that's how much the displacement of our object had. And these two are related actually. So Young's modulus. Young wrong. So, so Young's modulus is equal to the stress exerted over the strain. So if we know Young's modulus and we get the stress, we can sort of save time and find the strain, right? And you can do this, right? So the stress is 5 million divided by 2 times 10 to the negative 4, and that should give us what the Young's modulus is, which is 25 times 10 to the power 9, right? So that's how stress and strain are related. Cool. Yeah, if you guys have any questions, go ahead and comment, and I'll get back to you as soon as possible. Yeah, if you want me to change anything about what I'm doing, or maybe you can't attend my office hours, just let me know in the comments, and I'll try to accommodate you guys as best I can. Cool. Have a good week.